Thank you so much for such a lovely introduction. It really mirrors my own sense of how wonderful it is to be here. And I'm just delighted to be here and spend time with you. I'll take a moment to mention I decided to have office hours Monday afternoon. I think I put 1 to 2 on my door. So please come by if you have any question or whatever is on your mind. The door is open. Door is always open, but it's open especially from 1 to 2 on Mondays. Okay, so for this talk, I wanted to put some ideas that I've been thinking about in front of you. So this is a little different from maybe what might be a standard talk where sort of well-developed research ideas are presented. These are thoughts. These are directions. I'm going to try to convince you that there's a historical trajectory here for some of this that I think is really pushing us in certain directions as research scientists. And I really want to convince you it's very, very important for our research. So Tillman is exactly correct. So I would like to focus on AI-enabled scientific research. In particular, how do we know it's right? Okay. So here's the goal of the talk today. I'm going to start with where we are. Okay, this is a recap of the open research movement or the open science movement. And this is what I think has pushed, in part, many of the changes that have brought about these fundamental changes about how we do research. Then I'd like to talk about in more detail, what does it mean to leverage AI in scientific research? Why is this even a problem? What's going on? And by the way, giant tech companies are doing this all over fields that used to be ours. And why can't we do it too? What's wrong with that? If we buy into this world, that that's the type of research we'd like to do, or where we would like to bring our fields, this, I'm going to try to convince you, is deeply disruptive to our scientific norms in ways that it's worth thinking about and worth articulating who is winning when we make these changes, who's losing, and what does the scientific method mean when we have these AI-enabled tools that are regularly relied upon for the production of scientific findings. And we have to confront these questions. It's coming. We're doing it. That's section 2. Okay, and then to end on a little more of an optimistic note, I'm going to sketch where I think this is going. I think what we're going to end up doing, and I think the right way to conceptualize how to do this kind of research and how to share this kind of AI-enabled scientific research, is to think about what a digital scholarly record really means. I'm going to give you a definition when I get there, and I'm going to try to convince you that it makes complete sense in the context in which our entire research enterprise is moving, and is something that if we're just a little bit careful about how we do it, we could end up with actually a really great and useful object. So that's my goal for today. Okay, Tillman went over my background, but I have a slide in here in case it is not recorded. I think people on Zoom can now see the the summary of my life. I graduated with a PhD in statistics in 2006. David Donahoe was my advisor. And as Tillman mentioned, I also have a master's in legal studies from Stanford Law School and degrees in economics as well. My undergraduate was in economics. Okay, so open research in academia, what has been going on? Why am I even raising this issue? I believe there's a transformation going on that is in part due to how routinely we share digital scholarly objects now. Okay, so there's many sources for why this is happening and why this is accelerating. One, we've been obsessed, almost globally obsessed with data sharing for the last several decades. You hear about open data, you hear about the transformational value of data, big data, and so on. It's almost like we've had this, cultural obsession about data sharing and how grand it is and great it is. It has been going on for several decades, and we have been capitalizing on that in our research. going along with the data sharing is the development of infrastructure. Now, the scientific community hasn't developed all the infrastructure ourselves. We certainly developed many, many tools. But if you think about the infrastructure developed just by the use of the humble cell phone, right? We have cloud infrastructure has emerged from just the advent and the spread of mobile phone technology. Nothing to do with science. I would imagine almost everyone in here is using the cloud for science in some way. And this is a direct descendant from the impact of the mobile phone and the infrastructure and technology it takes to support those mobile phone networks. We've seen in academia, and I have some examples, it's much more common now to just share the code, share the data that underlies your results. When I started researching in this area, almost nobody did this. It was really weird. Maybe to do it was really weird. You maybe had some pioneering researchers in 1998 or 2001 that would put tar files on their own website. It's about as advanced as it was back then. Now, regularly, if you're publishing in, I don't know if I can say most journals, but certainly many journals and many high impact journals, it would be very weird not to expect to at least share the data. Code lags behind data and sharing, but then you have also researchers, regardless of what the journals are doing, working openly on GitHub. It's also, imagine this is true for many people here as well. Okay, so that's two factors going side by side. Now we have the infrastructure development that we're leveraging in the scientific community beyond cloud infrastructure and so on, the sort of massive infrastructure that was developed for the mobile phone networks. Things like GitHub, which didn't really come from science, came from open source software development, leveraged all over science. Things like NIH, National Institutes for Health, geo infrastructure for housing data and housing code, NSF's Public Access Repository, PAR, where all the papers that are associated with NSF grants get put. So this is just infrastructure that's been developed. Ones we know, Kaggle, Colab, probably people here have used all of these tools. And so this is the infrastructure that is now just part of the fabric of how we do research. Okay, so why am I talking, what does that have to do with AI? Okay, so the large language models are trained on this open data that we've spent decades being obsessed with and creating all of these open data sets. Without these open data sets and the availability of the open data, there wouldn't be LLMs the way that we use them today. We wouldn't have the sort of AI models that we're used to having. So I put an example here. So this example in the little table is taken from the first Llama paper. And you can just see the data sets that they're training on. So Common Crawl, people probably this is a research-oriented company that routinely crawls the web to create research data sets. Google relies on it, Llama relies on it, and so on. GitHub's crawled Wikipedia, books, archive, Stack Exchange, things we're all familiar with, open data. And then there come our results with the LLMs. Okay. Another deeply disruptive change, the workflows you create that produce the results that you're publishing in the journals or sharing at conferences now have somehow become very important digital objects in their own right. This is new. 20, 30 years ago, it would have been enough to explain your methods in English in a paragraph or two in the paper, or show your proofs, for example. Now we have already in digital form, I would say fairly, usually easily shareable. And these workflows are incredibly powerful. So if they're done right, other people can run and generate your results and check things, or take modular pieces of the thinking and the algorithms that you've used to generate your results. First-class digital objects, and probably for young people, you didn't even think about it. It's just so obvious that this is the way you would do and share your science, and you'll grab other people's bits and pieces that they've shared and use it to accelerate your work without even thinking about it. But actually, that's a huge change in the way science is done. Okay, so that underlies model estimation, prediction, and it's just becoming like breathing in scientific research. Okay, so these changes have been driven in the academic community by a proud maybe 50 years of advocacy for digital research object sharing. There's books I could talk about here. Very briefly, I'll give you a few snippets of how important this has been. Many reports, National Academy of Science and Engineering reports, scientific societies have had committees, reports, they've decided on badging, whatever it is that they want to do around digital research object sharing. It comes down to the topic of this talk, verifiability. If I'm not able to get to the data and get to those steps that got to your results, in a sense, you're asking me to believe the results because of who you are or because the results look like other results out there. We all know that's a fail. Right? So there's also been a lot of grassroots efforts around policy changes, in particular at the journal level, at conference level, around you must share the data, you must share the code. This has evolved over the last decade. It used to be, if you publish in my journal, you're making a promise to any reader, you'll make the code available, you'll make the data available. That went about as well as you would expect. Now there are deposit requirements before publishing, I would say in most of the high impact journals. And it's so interesting, it just goes across fields as well. So the fields are becoming more computational, leveraging more data, more compute, and also coming up to speed with how to make these steps transparent or verifiable. Okay, community standards that have been developed, Open Science Foundation, National Institute of Standards Organization, ACM, IEEE, all and others all have had efforts to develop recognition, right, and incentives around badging, what the standards are. If someone says share your code, if you've never done that, what does that even mean? It's a very real question. And so there's been conversations to help shape out what it means to actually successfully share some of these digital objects. So it's just a smattering of things that have been going on. The theme here is that researchers will continue, as they have for, I don't know, back to the beginning of scientific research, to just reach out and in an entrepreneurial way, use whatever tools are lying around that they think are going to help their research. We've always done it. We're always cash poor. We just sort of grab things that are out there. We're very talented and we make it work for us. And that's exactly what is happening here, exactly what is going to continue to happen. So we need to be ready for it. Okay, the font is a little bit small here, but I just wanted to give you an example. Back in 2016, I helped organize a workshop on code and modeling reproducibility. So like almost 10 years ago now. And we had a number of recommendations around sharing data, having persistent links to the data and code. So you're not reading a paper in 10 years and clicking on a link and it's dead. So we're trying to avoid that. Citing should be a standard practice if you use any of these shared digital objects. Documentation, open licensing, engaging the funding agencies, and journals doing the reproducibility check. And so we've made advances on almost all of these. Okay, and probably one of the most important milestones was the 2019 National Academy's consensus report, which had about 15 members and went on and I was part of the committee and it went on and on for many, many months. But the reason for that is because as soon as you start thinking about what reproducibility means in anything but the highest level possible, you start thinking about the different fields, right, or the different application areas, and then things are suddenly quite different. The pain points are different. What's easy for one set of people is difficult for another set. So it becomes extremely variegated very quickly on how to make progress or even what this really means and how to share ideas. So it took us time to speak to these different communities, and we have many use cases in there. The most important thing, in my opinion, that came from this report was, in some sense, a standardization of definitions. Prior to 2019, there was a lot of confusion around what reproducibility meant in science and what replicability meant in science. Different fields would use them oppositely to mean the same thing and so on. So it was inhibiting a lot of these conversations. We said reproducibility, get consistent results, same data, same code, everything the same, basically. Can I redo what you did computationally and get the same results? So that was the definition of reproducibility. Replicability, which is in some sense what we're a little bit more used to when we think about the scientific method going back hundreds of years. Can I take the same research question you had or the same hypothesis? Maybe I have another way of getting at that answer. It might be newly collected data or a different method or both, or maybe a slightly different hypothesis. If I get something that's consistent with what other people are getting, then it starts to be more credible. So sometimes I have had questions, who cares if I can run someone else's results? Isn't replicability really what's important for science? And I think on its face, it's a very reasonable question. But if you think about it a step deeper, first of all, rerunning someone else's sort of workflow or sort of pipeline of code that led to results is not at all easy. Generally speaking, you put a lot of kind of work into doing that. But let's suppose you can do that. Replicability, where you have the two studies producing, let's say, consistent results. You still need reproducibility because you need to understand why they're differing, right? Even just numerical sensitivities, you're never going to end up with some results that have the same, number of decimal points and they're exactly the same. So you want to understand where that noise is creeping into the system. Are there errors creeping into that pipeline and why it's different? You need reproducibility to be able to do that. Okay, so I think this was something of a watershed in 2019. Okay, so the topic of this talk, AI, it's extremely different. So large language models are trained entirely in industry settings, right? And only by the very largest tech companies, right? There is no academic institution that has trained an LLM on that scale with that level of success. So what does that mean? It means our leveraging of the LLMs, we didn't train that model. They're deeply complex in terms of the layers, in terms of the models, in terms of the fitting, in terms of just the complexity of the nodes and the connections, on the order of billions, right? And so right away, we look at this model that we didn't even train. It acts as a black box. We don't have a hope of understanding some kind of reasoning or interpretation through there. I think there are some advances that are starting to look at, some types of responses, but we have to sort of treat it as a system that we're trying to understand. It's totally different to how we used to do models with smaller data, smaller compute, where we would have some expectation of understanding what the meaning of a fitted coefficient was, how it impacted the result. We would learn something about the natural world through the fitting of the model. This just blows that way of approaching scientific knowledge discovery out of the water. So it's totally different for us. Okay, yeah, so I have a few examples here. So ChatGPT-4 trained on 20,000 GPUs for 3 months. That was in 2022. I don't know where we have 20,000 GPUs. Academia. Maybe we could find 1,000. Gemini Pro, when I wrote this is a few months ago, so this is probably a few months old, this statistic. Trained on 40,000, or if you're using Ultra, trained on 80,000 TPUs, the custom tensor chips developed by Google just for training these models. So the scale of compute is just outstripping anything we're capable of in academia for this type of model production. It's estimated in 2023, the AI industry spent 50 billion just on the GPUs, not even the people. Okay, we're not able to reach this. Yet, I'm going to guess almost everyone here has somehow used one of these AI models somehow in either querying a data set, querying models, or understanding a theorem, or whatever it is. And so already we're just leveraging these models, even though they're black box. Okay. And it's increasing. Okay, so what does it mean to leverage these AI, leverage these digital assets in scientific research and discovery? Okay, so I think today these are just unstoppable forces, regardless of ethics or a variety of other concerns that we might have. They're highly complex. highly complex computation, data, integrated scientific workflows. It's very similar to the type of work that we do. Our expectation is open, transparent, re-executable pipelines, likely machine learning pipelines. We just talked about at the beginning of the lecture how many journals require this. So what are we doing with ChatGPT if our results rely on this and we're publishing in a journal that has open data, open model requirements, open code requirements? It's a good question for the editors. Okay, and also we have open data. Okay, so how is this research being done? Now, if you look at what is happening kind of out there in the wild or in industry, they do a type of research approach that is not, we haven't traditionally done it in academia. There are pockets that are important that I'll talk about, but what they use is the common task framework, and you've all seen it on Kaggle, right? That's a good example where there's a certain goal in mind, there's holdout data, there's shared training data, and then, you know, people just kind of go crazy with the workflows, and the models that do the best job come out as winners, right? So that's kind of the common task framework, a kind of Olympics of benchmark competition between machine learning models using shared data, and they redeploy complex scientific discovery workflows. They're very often leveraged by the results of LLMs, which are of course opaque. Things like feature selection or data processing, which are for reasons I don't fully understand, are often just sort of skipped over. They're actually incredibly important parts of machine learning, but oftentimes these get turned over to LLMs. Okay, so research is shared natively as digital objects, or not at all, with this newish method of doing research. Maybe a PDF gets published, maybe it doesn't. You can easily win Kaggle, never really publish a paper. And I'm just going to go out on a limb and say probably many of these people are young, more computer science oriented, and they're having phenomenal results with this approach. Okay, just a minute, if you indulge me with a minute of background on the common task framework. So this goes back to 1986. There was a DARPA program manager named Charles Wayne. And what he did is he had this idea of the common task framework, and he implemented it in his programs, and it reinvigorated what was then a dead field of machine translation. And well, I'll get to it in a moment, but oh no, here. Okay, so the machine translation had a lot of activity up until the 70s, and the problem is there was no progress. So what Charles Wayne did is he said, if we have a well-defined objective evaluation metric, okay, that's think of benchmarks in Kaggle, for example. It's exactly the same idea. So the objective is well-defined. And then whether or not a researcher has met the objective with their research is evaluated by a neutral agent. So in Charles Wayne case, and in reinvigorated machine translation, he chose NIST, the government agency, a federal government agency, to hold out the test data set secretly. So none of the researchers saw this. And then they would submit their code to NIST, who would run it on the test data set and let them know how they did. Okay, now what that did was it allowed people to, since it was benchmarked, they could start to learn what methods worked well, what methods did not work well, right? Before that, there were a lot of complaints in machine translation without this established and shared objective benchmark. One of the giants of the field, Pierce, in 1969 wrote this report railing against glamour and deceit from mad inventors and untrustworthy engineers. They were setting this variety of benchmarks just on whatever they were doing. No one could compare the results, and we weren't making progress. So in this case, participants revealed their methods to this neutral agent, NIST or whatever it is, and when the evaluation results are revealed, the idea is simple, clear, sure knowledge is gained. Okay, this is so phenomenally successful. I mean, it's why we have Siri, for example, and a variety of other, like Cortana, who I think they may have ended the program, but all of these machine translation programs came from, the genesis is from this DARPA program manager, Charles Wayne, and actually his program. Okay, the detailed evaluation plan for the Common Task Framework, it's done with collaboration with the researchers. People know what's going on. Before you do anything, like for example, peek at the data, that's published. Then the evaluation software is written, maintained by that neutral third agent, also published. Okay, so the researchers know exactly what's going to be run and exactly what the evaluation is going to be. The data is shared among the researchers, not the holdout set, just the training data. And then the methods developed on the training data are then applied to the test data periodically, and we can make magical progress. Okay, so let's think about that, because this is how so much research is being done, right? Maybe we see it less in academia, but look and see what's going on with the big tech companies, with the leveraging of the LLMs, and this is the mode that they're carrying out the research and being incredibly successful. So LLMs get leveraged routinely, for example, for metadata completion, for integrated accessible data sets. Merging data sets is incredibly hard, but it's so tedious, right, to sort of match up these data sets. It's ideal for an LLM. The research that's ongoing has standard benchmarking of clear and concise solution definitions. You know when you win. And then as people are doing this, so think of Kaggle, people sharing their workflows. These can get crawled by bots or by LLMs. And best solutions can be found or reapplied in different data sets and so on. Okay, so here's what I wanted to say. If our own research or research in general is going in this direction, and I tried to make the case that leveraging LLMs, using these methods of approaching scientific research and knowledge generation is an unstoppable force. Just trying to convince you of this. So what impact does that have on the way we do academic research today? So I've developed a few questions to help shape thinking about this. So for example, is there research that's being carried out that's important, and it's difficult to define those benchmarks, or maybe impossible to define these, objective benchmarks that everyone agrees on? How do we choose these benchmarks and what problems to work on, especially if they're going to dominate the directions of research? In this modality of research, with any change, there are winners and losers. Maybe some people will thrive in a more competitive environment, will sort of working against benchmarks and so on. Maybe this is not comfortable for some people who would otherwise be great researchers, but they're suddenly in this world that they don't love. And one of, I think, the most interesting, well, they're all interesting questions, but one of the most important questions, suppose all of these pipelines giving results against this benchmark are black box. There's some kind of input, right? Shared training data, whatever it is. And then there's some output. Okay, we can evaluate the output against those benchmarks. All seems great. But what happened in the middle? Okay, so what happened in the middle used to be what we called science, right? It used to be how we understood the natural world. We would learn something. Nobody cares about that anymore. Okay, I won the benchmarking competition. Okay, great. But what does that really mean? I can't understand this chain of reasoning that led to the results. And it's not even a criticism. There's just no chance of understanding that chain of reasoning. This is done for the bots, and it's done for the LLMs. It's not done for human knowledge anymore. In a sense, we're sort of told, okay, this is the winning answer. And so how trustable it is comes down to those guidelines on how we decided that that was the winning answer. You have to trust the process in some way. totally different to how we have thought about what science is for hundreds of years. So we are disrupting our scientific norms very deeply. Okay, so let's go way back in time. So you probably recognize this is Robert Boyle. The scientific record started in the 1660s. So many of you have probably heard of the Invisible College. So this is the founding of the Royal Society of London in the 1660s. Just essentially was the sort of scientifically minded, it was old white guys, you know, there wasn't anything else going on in those days. And they were discussing their ideas. And so it mimics some of these criticisms in a way that Pierce had about glamour and deceit, the mad inventor, the untrusty engineer. They didn't use that kind of flowery language, but what they did is they, especially Boyle, started to realize that if there weren't standards around sharing and communication, progress wasn't going to be made. You weren't going to understand what other researchers were doing. So the first set of standards around reproducibility was done by Robert Boyle. Okay, so the first journal started because these, you know, scientifically leaning gentlemen were writing each other letters about what they were doing. Okay, and so that sounds a lot like writing journal papers. It was the start of the journal paper. And they got organized because there was a secretary of the Royal Society, Henry Oldenburg, who just got tired of organizing all these letters and just kind of turned it into this, he got this idea of this journal. So this is a picture of the cover of the first journal. It's a little bit hard to read, but it is so fanciful. The philosophical transactions, giving some accomplishments of the present undertakings, studies, and labors of the ingenious in many considerable parts of the world. I guess they were nothing if not ambitious. Okay, and so and Boyle wrote in his books these series of standards. So he had a book in 1660 called New Experiments, Physico-Mechanical, touching the spring of the air and its effects. So I believe Robert Boyle was entirely dead serious with these titles, but you know, in 2025, they sound extremely fanciful. Standards for scientific communication were set. You had to put in, one, enough detail on equipment, materials, and procedures for reproducibility. Two, you had to have communal witnessing. So you've done some experiment. A lot of work was expended in those days around the vacuum pump and creation of the air pump. So you had to do communal witnessing, show people you could create the vacuum or whatever it was. And then that was an important part of credibility. He also demanded exhaustive details on your experimental settings, false starts, failures, etc. Sounds very similar to our kind of p-hacking discussions that we've been having for the last 10 years. Boyle says, in certain physiological essays and other tracts written at distant times and on several occasions by the Honorable Robert Boyle, he says it is much more difficult than most men can imagine to make an accurate experiment. Okay, so we know all this. We've known it for hundreds of years. Okay, so these standards for scientific communication or scientific publication started with Boyle, 1660s, enough detail on equipment, materials, procedures for reproducibility, communal witnessing, and the exhaustive details on what you did, what went wrong, and what your path to success was. Okay, this evolved in the roughly 1900s to our standard layout for the journal publication. There's a format, right? And every journal will tell you what format they want. They're all somewhat related. They all have some kind of introduction. They all have a methods section, results, discussion, right? And you won't get published if you just leave out the methods section. We kind of got rid of communal, I mean, we have sort of peer review a little bit, but we sort of got rid of communal witnessing. Okay, so where are we today going forward? An entire phase transition. We now have executable workflows, links to corresponding data, and links to the results, and open accessibility. Completely different. What are we losing? Okay, here's what we're losing, at least of what I've come up with. You guys might have other ideas too. Authorship. Authorship is so important in scientific research, and particularly in academic scientific research. Boyle talked about the communal witnessing. People would stand around. We know who did what and where the credit was supposed to go. We know who wrote up the experiment and so on and who did it. So LLMs, other large language model leverage discoveries entirely break this chain of authorship. So we also rely on this for understanding where to give credit to different scientists, how to promote, whether or not we should give prizes, whatever it is, who's important in our community and so on. It comes down to authorship. I mean, if you want to test that theory, just forget to cite someone's, they'll go crazy, right? It's so important. Okay, so when you have AI leveraged executable workflows, who's the author? If you've relied on AI for something like metadata completion or something like feature selection or something like this, or even a more sophisticated part of your modeling process, it's not all your thoughts, right? And it used to be when you wrote a paper, you'd bring it, you were rewarded for bringing in and building on thoughts and results and so on that other people have had and other scientists have had. That's the methods, that's all part of citation. But now we're kind of like, I don't know how to solve this with LLMs. How do we know what ideas that we're building on when we're leveraging the LLMs? Who do we give credit to? We get some results. What those results advance, do we know? We're just sort of coming up with these random black boxes. Okay, and the thing that fascinates me, as I alluded to earlier, this isn't human reasoning, and it's not meant to augment human reasoning anymore. It used to, at least I think science used to, is about discovering the natural world and understanding how it worked. Now we're querying and getting results. Kind of like Googling or something. Okay, so knowledge becomes a utility, and it doesn't become something that is associated with understanding anymore. So here's our AI-enabled future. Results are believed correct because we trust the discovery process. So here's our task. We can't leave this up to the big tech companies. Right now, that's where it lands. Our task, I see it, is to develop a scientific method for the challenges. So is the quantitative goal of the challenge problem sufficient to support the scientific conclusions? You have to sort of make that argument. You need a meaningful definition or meaningfully precise problem description, some justification for the correctness of the benchmarks you chose, some justification for why the data you're using is even appropriate to solve that problem. This isn't how we think today, and it's not how we train our students. Some problems are just going to fly forward with this approach. Other types of scientific research is not as suitable for this approach and probably will falter. Thinking about what our data needs are to produce the results is something that's already coming up in LLM discussions about how the different LLMs are trained and what data sets they're trained on. Okay, so the data evaluation for scientific inference, I believe this is one of the factors at the heart of trusting these results. I'm just taking it for granted that we're going to have black box results. It's turned my career, or sort of my research thrust over the last many years, kind of on its head, because I can no longer really advocate for transparency. It's literally impossible. But maybe I can have more trust in these black box results if I understand how well the data set that was used as the input or as the training data really spans that true underlying population of interest that I'm looking to learn something on. Sample representativeness, let's say something intelligent about it. And then we can understand what the limits of the results are, where they can be applied, or what extrapolation means, like when are we going too far? What's the test set sampled from the input data? Is it a new sample? We see these types of problems come up with cross-validation. We see this come up with data generated in different labs and so on. Is it hived off the same? Is the test sample hived off the same sample? Or is this a new sample? Likely much more variable. And how do we understand the variability in the sources of error? I think these are all part of that question about verifying AI-enabled results. Okay, so here we are. Convergence and the emergent digital scholarly record. Okay, what do I mean by that? So if we take it for granted, we've got our social obsession with open data and sharing data that's been going on for a few decades. We now have, it's not quite as advanced as the open data conversation. We have lots of open code, right? We have these expectations of sharing an executable workflow. And in younger researchers, it's automatic. They just do it anyway. Can we integrate data, code, results into some kind of coherent form? Have you ever thought about how frustrating it is with the current scholarly record, right? Whatever library you go to or whatever it is, and you should look for papers and journals and so on. How do you find stuff, right? You can't query that scholarly record and say, okay, give me all the papers that use this particular input data set, whether it's metrology or image processing or whatever it is. There's very famous data sets out there. Can't search across data set. Give me all the results that relied on some certain machine learning algorithm. Also can't do that easily. And this is how we do research, right? You start from data. You start querying, or it's not the right word. You start kind of poking at a particular method and how can you improve it? And so you want the literature associated with that. Okay, so the dream, since we already have shared data, shared code, shared results in natively digital formats, why aren't they intelligently linked and integrated? You could search easily for data sets, for methods, and so on. We'd get a lot more efficiency. So I'm imagining it's sort of little pieces of it sort of exist, but it doesn't exist as a coherent whole yet. But I'm imagining a verifiable, extensible data set in a systematic and open way that facilitates regeneration of computational results, models. I can look at something and I can rebuild it because the executable workflow is there and associated with it. Once I have all these data together, whether it's the workflow, input data, results, and so on, how much easier would it be to compare and reconcile different hypotheses and different results? There are many fields where you sort of think of sort of hypothesis-driven science, where fields kind of will start to coalesce. They'll sort of learn that maybe this hypothesis isn't really the right one, or maybe this one is. In my experience, many fields, they just kind of never do the coalescing part. They just sort of end up with splinters where one group is sort of their research points to this hypothesis. Another group, their research points to that hypothesis, and never the twain shall meet, right? Which is, it's when you get into the weeds, that's what we're doing. But from 50,000 feet, we're supposed to be kind of defeating hypotheses and reconciling and learning from each other. This would be almost like a bot could do it if we had the integrated data set to allow us to do that. Bots and people could also re-implement methods on new data. We have, time goes by, we have updated data sets. So that's something that could automatically happen. We could see how results evolve, update our methods with new methodological developments. Evolve our benchmarks, right? I don't know what the rules are, or sort of best practices around creating benchmarks. So we'll learn them and we'll just keep going and we'll do better next time. And that will be part of this digital scholarly record. How can we assess our models, inference methods? We have our standardized test beds embedded into this system. Okay, and I'm also imagining that if it's a coherent database, it could be wrapped in reasonable policies, right? Around privacy, around ethics, meta research could be carried out on the scholarly record. What fields are, or what types of work accelerates faster or slower or whatnot. And that kind of research, it's no reason we wouldn't do it. It's just really, really hard because the information is just so diffuse. Okay. So whether or not we affirmatively take this on and think about what a digital scholarly record means, how we can contribute to it, how we can leverage it, the robots are out crawling. They're kind of sort of building up some distributed version of the digital scholarly record anyway. So here's what I imagine for 2050. Scholarly record is some collection of organically connected frameworks, training data, leaderboard results, benchmarks. Correctness of a result is not established by reproducibility, transparency, human verification, for example, replicability, redoing that experiment, but just by direct checks on the methodology. Verification of conclusions is by direct experiment on the black boxes that produce those conclusions. How sensitive are they? What happens when I change the data? Okay, that looks reasonable. Investigation of black box discovery methods, opening us to a knowledge of past and future. So that's a callback to Bacon's new knowledge, where this idea of inductive reasoning is what really kicked off the Invisible College in 1660. It was such a interesting and baffling concept for those learned gentlemen back in the day, and began our modern scientific enterprise. So I think we'll see something like that happening again. Okay, so now we are not touching the spring in the air like Robert Boyle did. We're just going to generate a collection of useful results of work. So the chain of logic behind the discoveries is accessible via the LLMs, and code that's impenetrable to us, and some kind of specialized scientific discovery pipeline querying tools that I don't know whether they've been developed. Maybe they're out there, but if not, we're going to develop them. Okay. So this acts like a traditional scholarly record in the following ways. It will form a locus for research communities, share ideas, get feedback, improve the work, agree on priority, resolve debates, all these sort of functions of our regular, normal scholarly record that we're using today. AI can allow us to document and trace contributions and authorship. We just have to think of a new way to do that. And how many people here, probably everyone, has used GitHub, and it's occurred to you that, well, if I use GitHub, I don't really need to have a separate citation section. It's just kind of obvious what code I've built on. It's all built into the way that I'm developing my own code. So we start to have new ways of understanding authorship, exposing our pipelines, having automated tests. It's become normal. It's not something we do now. And then automated discovery verification through this replication and also reproducibility. Okay. Integrating our computational knowledge to get a queryable and extensible open knowledge base. The idea is we all can query it. It doesn't sit on Google's servers. Synthesizing computational and data-enabled discoveries, reusable pipelines, reimplementation of methods on new data, all these things that, you know, if you should think about a student starting a new project, that's the types of things that you would just start out with. Comparison, reconciliation of different conclusions, benchmarks, understanding how to do it better, understanding what test beds are appropriate to learn whether or not we're getting close to something that's workable. Development and application of policies regarding data privacy, ethics, and so on. And maybe we automate more and more of this list. Okay, so how do we get these results? Well, no one knows how, and nobody's even asking how. So think about Kaggle, just as the example that I've been kind of picking on Kaggle a little bit throughout. There's many other sort of infrastructure websites, tools that also organize these sort of Olympic styles methods of discovery. But in any of those discussions, nobody is asking why this works. You just sort of come out on top, and that's great. So what we're doing is focusing on results that benchmark performance goals, not focusing on something that we can actually understand or reason why we got these results. That means our guardrails for knowledge production, which are not there today, because this is a new type of knowledge production that I'm talking about, they become very important because we can't rely on things like peer review, disclosure of transparent methods, a human verification, independent reproduction of findings. It's all happening automated, or it's not happening at all. Like, for example, peer review, if the PDF is an afterthought, it's just not getting reviewed in a traditional way. Okay, so obviously this involves all sorts of stakeholders across the scientific community. It's not something that one researcher sort of starts to solve. It's all interconnected with funders, the researchers, publishers working together with the libraries, academic institutions, regulatory bodies, scientific societies, the same players that we've seen come up over and over again in the open science and open research discussions where we started the discussion today. I did want to mention that there's been some efforts at KIT around reproducible research pipelines. So in the end of January, I gathered a group of students with lots of support from KIT faculty, a group of students to understand what does it mean to produce these workflows at KIT. What are they finding easy? What are they finding difficult? And what improvements could potentially be made to help facilitate this idea of the production of these executable workflows? And I have some findings, so they're being written up into a report, but that's part of one of my research goals while I'm here. And just to conclude, I think we're headed towards this world where we're going to be dominated by the challenge problem framework for scientific discovery. Large opaque models will be how we make our predictions. We're leveraging massive compute and data infrastructure, and we also will be leveraging AI. So the implications of leveraging AI, we need to be careful around authorship and accountability, entirely disrupted. We are generating these non-human accessible chains of scientific reasoning, which means we can't rely on this for correctness. And yet there's an emergent digital scholarly record. I would like to see a proactive, purposeful digital scholarly record as a database emerging. If it doesn't, we have what I was describing as that collection of loosely linked detritus of scientific objects, and we may end up there. Okay, so I see that as our big task, developing a scientific method for AI-enabled research, because we're going through a phase transition. So just to conclude, I asked ChatGPT-4, give me a robot touching the spring in the air. This is what she developed, okay, and said, oh, here's a surrealist style drawing of a robot touching a spring in the air. So I don't think ChatGPT had read any of Robert Boyle. The robot is depicted with abstract and distorted features set against a dreamlike landscape with flowing surreal shapes. The spring maintains a twisted helix-like form to add to the surreal ambiance. So I don't know what Robert Boyle was thinking. Maybe he's thinking about robots touching the spring in the air. But this is where we are now, from 1660 to 2025. Okay, I would be very delighted to take questions if you have any.